1.2 Uncertainty in measurement. Every measured quantity has its uncertainty or reliability. When mathematical operations, for example multiplication and addition, are performed on these quantities, we should not expect that the resulting quantity becomes more reliable than quantities used in the calculation. Two general rules are adapted. The first rule is when quantities are multiplied or divided, the number of significant figures in the final answer is the same as the smallest number of significant figures of the quantities used in the multiplication or division. The second rule, when quantities are added or subtracted, the number of decimal places in the final answer is the same as the smallest number of decimal places of the quantities used in the addition or subtraction. Let's take a look at this tutorial question in order to learn on how to calculate uncertainty in measurement. For reference, I will put these two rules under this question. The radius of a solid sphere is measured to be 6.5 plus minus 0.20 cm and its mass is measured to be 1.85 plus minus 0.02 kilogram. Determine the density of the sphere in kilograms per cubic meter and the uncertainty in the density. The question requires us to calculate the density and the unit must be in kilograms per cubic meter and also to find the uncertainty in the density. If we take a look at the radius given, the unit is in cm and for the mass it is in kilogram. So firstly, we're going to write down the equation to calculate density. Rho is equal to the mass over the volume. Because the provided information is the radius, so we will change the volume into 4 over 3 pi r cubed, which is the equation to calculate the volume of a sphere. Now we can substitute the value. For the mass, it is 1.85 kilogram over 4 over 3 pi multiply with the radius. The radius, as you recall, is in cm. So we need to change to meter. 6.50 times 10 to the power of negative 2, and then we give power of 3 to the radius. The volume is equal to 1608.211077 kilogram per meter cube. Now we will calculate the uncertainty in the density. So firstly, I'm going to write down the equation that we use to calculate the density, which is rho is equal to m over 4 over 3 pi r cubed. To calculate uncertainty, we must firstly calculate fractional error. Delta rho over rho is going to be equal to the fractional error due to each of the parameter that we used. The first one will be the fractional error due to the mass, and then we're going to add with the fractional error due to the radius. Radius is to the power of 3, meaning that r multiplied with r multiplied with r, and because of that, the fractional error due to the radius will be written 3 times. We can simplify this by multiplying delta R over R by 3. Now we are ready to substitute the value. For the fractional error of the mass, it is going to be 0.02 over the mass, which is 1.85, plus with 3 multiplied with the fractional error due to the radius, which is 0.20 over 6.5. The value for the fractional error here will be equal to 0.1031185, and then I'm going to multiply the density with this fractional error. Now remember that the density, as we calculated, is 1608.211,077 kilogram per meter cube. So this value will be multiplied with the fractional error due to the mass as well as the radius. The uncertainty of the density will be 165.8363 kilogram per meter cube. Now we will be applying these two rules to our calculated values of density. Let's take a look at the calculated value of density. Because the operations are multiplication as well as division here, the number of significant figures in the final answer is the same as the smallest number of significant figures of the quantities used in the multiplication or division. For the mass here, the number of significant figures are 3. 3 significant figures. For the radius, it will also be 3 significant figures. With that, our final answer for density must also be in 3 significant figures. So I will be underlining the first 3 number, and then we need to round this up so that it suits these 3 significant figures. The value for the density can be written as 1.61 by rounding 8 here times 10 to the power of 3 kilogram per meter cube. For the uncertainty, as you can see here, these are addition of fractional error, so we will be looking at the second rule. When quantities are added or subtracted, the number of decimal places in the final answer is the same as the smallest number of decimal places of the quantities used in the addition or subtraction. The decimal places for the mass is 2 decimal places. And for the radians, it is also 2 decimal places. With that being said, our final answer must also be in 2 decimal places. We can write down the density is 1.61 times 10 to the power of 3 kilogram per meter cube. For the uncertainty in density, we will write it down in the scientific notation as well as in 2 decimal places. So the uncertainty in the density is equal to 0.1658363 times 10 to the power of 3 kilogram per meter cube. For the two decimal places of uncertainty in the density, it will be equal to 0.17 times 10 to the power of 3 kilogram per meter cube. Now we can write down the density along with its uncertainty together. The density plus minus the uncertainty in the density is equal to 1.61 plus minus 0.17 times 10 to the power of 3 kilogram per meter cube. So this is our final answer.